Hello, everyone. My name is Sharadha, and I'm currently doing my PhD at USC. Thank you very much for giving me this opportunity to talk about my recent work on earthquake cycles in fault band folds. Folds are spectacular features seen both in the field as well as in seismic reflection profiles. Folds provide a record of tectonic processes. They drive the growth of topography. The main motivation for my talk today is to bring structural geology and fault dynamics together in order to study the interplay between faulting and folding, because the dynamics of fault-related folding plays a very important role in crustal deformation processes. In this study, we connect the long-term deformation predicted by geology-based kinematic models like the fault band fold theory with the short-term deformation that occurs during the seismic cycle. We apply fault band fold model to rate and state friction faults so we can have a unified representation of fault slip and off fault deformation. Because without off fault deformation, the slip around fault bends would create a space problem over long time scales because mass is not conserved in the system. To avoid such unrealistic outcomes, inelastic deformation must accumulate in the upper plate around the bend. The active axial surface that is tied to the fault bend accommodates the folding and is responsible for the stable geometric configuration for long-term deformation. We therefore include the dynamics of axial surfaces in our earthquake cycle models to account for off-fault deformation processes. In order to explore the dynamics that emerge from a simple fault band fold system, we use a synclinal fault band fold, a single fault with two segments, an upper segment or the ramp that dips at 40 degrees, and a lower segment that dips from 0 to 30 degrees. We include an active axial surface that extends from the surface to the fault band. The axial surface represents the fold axis that bisects the angle between the two fold limbs. This is because fault band fold model assumes incompressibility of rocks and hence conservation of layer thickness, conservation of bedding length, and cross-section area of the hanging wall over long time scales. In the first set of experiments, we consider cases where there is zero cutoff angle. Cutoff angle is the angle between the lower segment and the incoming thrust sheets. In such a scenario, the local loading rate on the two fault segments is uniform. This is a very common situation for this type of geometry as decolomorph form parallel to stratigraphy, taking advantage of pre-existing weak bedding planes. This situation allows us to investigate the roles of geometry and friction. What we are exploring here is the shape of the fold by varying the angle between the two fault segments. In a second set of experiments, we vary the cutoff angle. Again, the cutoff angle is angle between the bedding, the incoming truss sheets, and the lower segment. The importance of cutoff angle is that it produces contrasting loading rates on the two fault segments. So the long-term slip rate increases on the ramp compared to the decolomorph, as you can see here in the case of synclinal fault band folds. Alternatively, the long-term slip rate can decrease in the case where the fault flattens or what is called an anticlinal fault band fold. First, we investigate the effect of rate and state friction parameters on a fixed geometry. The spatial distribution of the frictional parameters control many aspects of fault behavior. Different physical parameters control various different aspects of the seismic cycle, so we use non-dimensional numbers to identify the combination of parameters that control rupture dynamics and style. The non-dimensional parameter that we explore, here we call Ru, represents a ratio of the seismogenic zone size, which is the size of the velocity weakening region, to a characteristic rupture nucleation dimension. So you get stable fault slip and velocity weakening regions with low values of Ru because of the large nucleation size compared to fault dimension. Higher values of Ru give rise to chaotic cycles with through-going ruptures followed by partial ruptures of varying sizes. We're now looking at how the magnitude of the fault bend affects seismic cycle. Each column represents a fixed geometry, and each row has fixed frictional properties. In this case, the same rate and state friction parameters. We see that for the same frictional properties, the rupture style changes depending on the magnitude of the fault bend. For example, you see here gentle fault bends produce characteristic through-going ruptures, but larger fault bends show more complex or complicated ruptures with periods of acceleration and deceleration during the rupture or a foreshock main shock sequence. Rupture styles can change from segmentation with gentle fault bends to no segmentation to large fault bends. For higher values of Ru, partial ruptures in the ramp are more frequent and significantly larger in large fault bends compared to gentle fault bends. This is a summary figure that shows the relationship between frictional properties. In this case, we have the Ru number in the x-axis and the magnitude of the fault bend on the y-axis. Earthquake segmentation occurs at high Ru values, but the Ru value at which faults start to show partial rupture depends on the magnitude of the fault bend. Gentle fault bends show segmentation at lower values of Ru compared to large fault bends that show segmentation at higher values of Ru. This is because large fault bends have an overall higher shear stress in the fault and can create through-going ruptures compared to gentle fault bends that have low stress barriers for the same value of Ru. In contrast, planar faults do not exhibit any significant changes in earthquake segmentation with respect to Ru, even when the dip of the fault is varied. This shows the importance of geometric complexities in fault models that study seismic cycles using the rate and state friction law. So for the same Ru value and frictional properties, rupture style can change depending on the magnitude of the fault bend. Persistence of seismicity at fault bends and other structural gradients may be explained by these effects. We also find that all events on a planar fault originate from the deeper sections of the velocity weakening region or at the transition zone between velocity weakening and velocity strengthening regions, compatible with several previous studies. This is because shear stress accumulation is highest near this boundary. In this plot, the stars indicate hypocenter locations, and you can see that for non-planar faults, ruptures can initiate at various locations along the fault, depending on the state of shear stress on the fault, which depends largely on the magnitude of the fault bend. We also observe that large fault bends are more likely to produce shallow events than gentle fault bends. This may be an important consideration when studying megathrust earthquakes both on land and offshore. Fault structures with significant fault bends may be more susceptible to shallow events due to stress heterogeneities. These findings provide a theoretical context to understand the emergence of shallow ruptures at continental fold and thrust belts like Nepal and Taiwan, and at subduction zones around the world. Next, we look at the cases where the local slip rate on the fault changes with the cutoff angle. This is a kinematic effect of area conservation. This situation can arise when fault has additional bends down dip and there has been sufficient slip on the décollement to carry these non-parallel beds up to and through to the shallower fault bend. Alternatively, this geometry is observed when a fault exhibits a change in orientation. Here, all four columns have the same fault geometry, but each of them have different hanging wall properties because the cutoff angle between the fault and the incoming sediments are varied. So for the same geometry and frictional properties, earthquake cycle dynamics can change depending on the incoming sediments. For example, here, faults break in single through-going ruptures when the incoming sediments are gently sloping. As the incoming sediments steepen, ruptures alternate breaking the ramp and décollement, but no single event ruptures the entire fault. And for higher values of Ru, a wide range of ruptures break different segments of the fault, as expected. As reference time is controlled by the local slip rate, which itself is controlled by the geometry of the fault and the cutoff angle, significant changes in earthquake cycles take place as the cutoff angle increases. We observe complex earthquake sequences with a range of partial ruptures that break several parts of the fault before culminating in a through-going rupture. So for all values of phi, which is the magnitude of the fault bend, the complexity of earthquake increases as the cutoff angle increases. Therefore, cutoff angle and the associated ratio of loading velocity may have a profound effect on down-dip segmentation of a megathrust and rupture style during the seismic cycle. Also, as the magnitude of the fault bend increases, the effect of the cutoff angle becomes more prominent or important. Although our model with a single fault bend is not representative of a full megathrust, insights from this model can be applied to segments of a megathrust to understand fault dynamics. Both gently dipping thrust sheets with large fault bends, as well as gentle fault bends with steep incoming thrust sheets, are able to produce shallow events. If these shallow ruptures produce significant seafloor displacements, they could lead to destructive tsunamis. Even though the characteristic properties and dynamics of accretionary prisms of subduction zones are largely unknown, studies of shallow earthquakes that initiate or propagate near the surface often suggest frictional heterogeneities are the main underlying cause. Here we show that the deformation of the upper plate with active folding can lead to these shallow earthquakes. High Ru values are generally associated with seismogenic regions of the megathrust, and they host a wide variety of ruptures that are spatio-temporally separated. Paleoseismic records have suggested that some faults produce earthquake supercycles, where the fault breaks in a piecewise fashion before culminating in a through-going rupture that breaks the entire seismogenic width. Our numerical models with morphological gradients lead to a wide variety of rupture sizes and extent. Shear stress variations that arise due to both changes in dip and the resulting variations in long-term slip can lead to chaotic cycles that do not repeat periodically. Now, if this pattern holds true for more realistic 3D fault surfaces, it will be important to understand not just the geometry of the fault, but also hanging wall structure in order to better understand earthquake patterns. I hope I have convinced you that fault bends and associated off-fault deformation can profoundly influence earthquake-related processes, and that it is very important to understand the interplay between frictional and geometric controls on earthquake dynamics. Thank you.